Oh, no. What I'm saying here is if the loading applied at the point, if at the point when the loading is less than the critical load, that means the structure will be stable. And here you notice that there's no additional increase for the deflection. So the force condition here, that means the applied force when it's less than the external, is less than the critical force, the structure will be stable. And when it is greater than the buckling load, and the structure will become unstable.
Okay.
So that's what we derive from the second order derivative of the total potential energy here.
I'm also confused because I thought you said that the second derivative, greater than or less than 0, is for post-buckling.
I think there's a confusion here. Let me go back to this one. Okay. Right. So first, if your buckling load, actually what I show the curve here means what? That means that's the buckling load values. So one of them is this one stable curve. That means your buckling load will increase with the increase of deflection. So that's why I meant that in that case, your structure is stable in the post-buckling behavior. You remember that we talk about the cable structures, right? After buckling, what happens to the structure? Does it require additional force or does it not? So stable post-buckling means after the buckling, when you keep increasing the load from here all the way to this point. Now this curve is not an applied force, but it's the internal buckling load. So that means if I want to keep loading it, your PCR, the value of the PCR is increasing. That's what I meant in this graph. That means you need to keep increasing this. Every value here corresponds to a PCR. That's not loading, that's PCR.
I see.
In other words, in order to buckle it, you have to provide more force.
Makes sense.
But thank you for the question, and so I can clarify this. On the other hand, if you load it without any deflection and you will write this value of PCR, but if you have any additional deflection here, but the corresponding buckling load is not increasing but decreasing, right? And that means what? That means, of course, unstable for post-buckling. So here, these two curves correspond to changing values for the critical load. And the example that we did here, we don't have the changing buckling load. Here, the buckling load is just Ks over L. This buckling load is only here. So what we found by using the energy approach is to determine that if your buckling load doesn't change, and after post-buckling, if you keep the loading at the same level, and then the structure will be stable. But if you're increasing the loading level, and the structure will become unstable. And notice that there's one more thing, is every point in this graph, if you just draw a dashed line here, they are not the same as the PCR. Because when we analyze the PCR, we assume that there's no deflection here, right? So what's the value when PCR, when P equals PCR? That is when delta equals 0. But what's post-buckling? The post-buckling means when delta is not 0. So at here, you have delta to be 0. But right here, delta is not 0. So that's post-buckling behavior. And what we analyze in this case is not really the post-buckling behavior, but just the criteria to determine that whether the structure will be stable or unstable if you maintain the same loading level. So that's what we found in this case. But please do not be confused. Do not confuse this case with the previous illustration. Now we can bring this example a little bit back by removing the small deflection assumption. And this is the example 4. Well, okay, I believe it's 8:55, and we should come back and continue. All right. So the next example, example 4, is exactly the example 3, except that we are going to remove the small deflection assumption. So there's no more small deflection assumption. Theta is theta, sine theta is sine theta. There's no more approximation. In that case, I will not repeat the whole problem definition. You already know the result. So we actually worked this process in backward fashion. You already know that PCR is what? Is Ks times theta over L over sine theta, right? There's no approximation. It's just like this. So compared to the critical load that we found by using small deflection assumption, this is only different by a ratio. And this ratio is just theta over sine theta, correct? That's the only difference, which is this. Agree? And this is the result of what we call large deflection. So now let's look at that, how this ratio change. And unlike most people would think that, well, when theta is small, sine theta is small, so isn't this ratio, supposed to be like approach to unity? Actually, it's not. If you have a computer program and you draw this relationship, which is from 0 to 2 pi. Between here, somewhere here is pi. Right? And then we can see that what kind of behavior you're going to see. In fact, if the y-axis is this ratio, theta over sine theta, this one here. And this curve actually is nonlinear. This curve actually looks like this. It's going to increase from start with 0, like this. When it approaches to pi, it would jump, actually goes to infinity, and then another one comes back like this. And then goes down like this. And just give you a table, and here you have these two values like this. Just give you some ideas about how this value change between theta and also theta over sine theta. Let's look at these two. When theta is about 0.03 pi, the ratio between theta and sine theta is about 1.0017, like this. But when theta becomes 0.5 pi, this ratio becomes 1.6. And when theta is pi, what happens to this value?
It approaches infinity.
Yes, approaches infinity. Very good. And when theta is 1.5 pi, this value becomes negative 4.7. And what happens when theta becomes 2 pi? It approaches to infinity again. So this is the first example between our theoretical analysis and practical implementation. When we say small deflection, right? And I believe you trust my assumption earlier, but as an engineer, also many of you have taken my classes before, you know that we engineers do not like adjectives. When you say small, what do you mean small is small? Now in this case, what do you mean how small is small, right? So this numerical example shows you that when somebody tells you that this bridge has a small deflection and you want to ask a follow-up question, that is, what do you mean by small? 1 centimeter, 10 centimeters, or even a foot. So do not just trust small or large without asking what is the quantitative description of that definition. Okay, so this example shows you the difference between large deflection and small deflection. And I did not tell you that what is the range when we can start using small deflection assumption. That's because it really depends on how tolerable you are or your problem is with this ratio, theta over sine theta. If the theta over sine theta is less than 1.7, you think that's still fine, then your range for the theta is going to be up to 0.5 pi. But if the ratio theta over sine theta, you think that if it's greater than 1.1, I don't think that's small enough. I'm going to say that that angle is large. And then your angular range will be limited to less than 0.03 pi here. So that is the this example is about. Okay, and we're going to come back to the PowerPoint, which is here. Now, design philosophies, and this is a very, very conceptual level of description, and I will not get into the details, but just to give you some ideas about how structural engineers use different design philosophies. In fact, many of you probably have seen some of these from steel design. This is how it looks like. And let me go back to the note. So we'll go to page 15. We're going to talk about different design philosophies. The first one is what we call allowable stress design. It's called ASD.